Welcome back, guys. This video is about to just a summary about open systems and first law, basically. I will not dwell too much into second law in this summary, but some things are hidden. Okay, so yeah, because otherwise I should talk a little bit more or with more specific examples. Okay, so this is what it is. It's a summary. Okay, summary of machines. I would say of machine or equipment or typical thermal equipment or thermal machines, so that you can see how these things are modeled using the first law, basically. Okay, I will put also conservation of mass, but it's a very you will see that it's a very easy way to model. This is just a general view, okay? So please take that into consideration. Most of the problems of real problems do not follow this general view, but it's a good way to start this complex problem. You start with the general view and then decide if this your specific problem follows this general view or up to which extent they follow that general view. Okay, well, okay, so I'm going to start with the turbine. So the turbine, it's a machine that what it does, it expands something gaseous, whether it's a steam or whether it's a gas. A turbine, what it does is take the thermal energy of a vapor or a steam or a gas. Okay, it's not a liquid. Well, I know there are hydraulic turbines. I'm just saying that they work in some other way with other principle. And at the outlet, you have a less thermal energy from that substance. In the meantime, you are producing mechanical power. That's the basic idea of a turbine. With this, I will go to conservation of mass, which is m dot equals to m2. Okay, I'm just going with the summary. This is not intended to explain in depth of why these things are like that. It's just a model. Okay, and conservation of energy, let me just go here. Conservation of energy is actually pretty simple. It's the work equals to the mass flow. Which one? Well, either one, because these guys are the same. So multiply by H2 minus H1, okay? This thing is gonna be negative, okay? If you take all the numbers as it is gonna be negative, that means that the work goes out of the system, okay? Which is correct. So that's what it means, that the work should be negative. Later in the course, we will see that you can actually just take this as positive because you already know that the work is going out of the system, and then you can manage the signs without much problem. But so far, let's just take this as if it was negative. Okay, now let me just put assumptions here. So some assumptions of what I have done in order to get to these equations is that this thing, okay, or some assumptions that you should take into consideration is this. They are mainly adiabatic, okay? What else? I should say the changes in potential energy are around zero. Changes in kinetic energy are around zero or can be neglected. What else you can say? You can say that you can model this thing as if they were isentropic. This is not completely true, but as a good approximation, you can take it as isentropic. Okay, now with these assumptions, you get to the equations that we have seen. Oh, I just forget, but you can also add this into the mix. But we all know that in this course that we are taking, these things is most of the time, I would say all the time, this is true, okay? The steady state, that thing is true all the time. Okay, that's it. That's simply it for this turbine. I know there's much more complex things in order to design the blades of the turbine, in order to design or to operate it. It's much more work than this. But so far, in order to model this as a global machine, this is what you need to know. Okay, it shouldn't be that complicated. Um, at this stage of knowledge of the knowledge that we have. Okay, now I'm gonna go with compressor. A compressor, it's a machine that what it does, it will take at one some substance, I would say vapor or gas. Okay, you cannot put into this liquid, because if you put liquid, it has another name, pump, but not right now. This is not the one that I'm looking. So it will take out that same thing, but at the outlet. And in order to make it work, okay, you need to introduce work. If you don't supply a type of work, whether it's electrical work or mechanical work or something, this machine will not function. The turbine, if you put something with a high thermal energy and you lower the thermal energy, then you will produce mechanical power. So you don't need to power the turbine, it will give you power. But the compressor is exactly the opposite. You need to power in order to produce something to the gas or the vapor that you put in. Okay. What happened here? Well, what happened here? Yeah, I'm gonna do this. This is the general things that are happening inside here. I can say that T1 is higher than T2, P1 is higher than P2. Okay, so those are things that almost all the time that happen. Okay, now here in this one I would say that T2 is higher than T1 and P2 is higher than P1. Okay, so you increase the pressure, so they are basically opposite, compressor and turbine. Okay, I'm gonna put conservation of mass, and the conservation of mass is pretty simple. M dot equals to M2, got it, which is M dot. Just like take it like that. Conservation of energy is the work equals to the m dot times the h2 minus h1. Okay, and now this thing will be positive. It's the same formula as is in the turbine, but now the work should give you positive. Okay, so that means that work goes in, or the mechanical power should need to go in. Otherwise, this machine doesn't do anything. I was gonna say doesn't work, but it sounds like I'm being redundant. Okay, but it doesn't function. Now, assumptions here, my assumptions here are these ones. This guy is adiabatic all the time. Well, no, not all the time, but as a general rule, you can say that these are adiabatic. Changes in potential energy and changes, let's just put it in just one way. Changes in kinetical energy are around zero, okay? They don't, well, you don't care too much about them. You can say that this guy is isentropic and of course steady state. Okay, so you will see around this video that these things are very look-alike, or you can machines really look alike from one to the other. They are not the same machine. Nonetheless, the equations can be modeled at some point as the same as the other machine. Okay, so you will detect some pattern here, hopefully. Let's just move on and let's see about the heat exchanger. Oh, the heat exchanger is a little bit different. So heat exchanger. Okay, so for the heat exchanger, I will model this as a rectangle. It's just a box that you put into something. Okay, I'm gonna call it 1, and this is gonna be 2. And in there, this thing is flowing. Okay, so maybe it's a substance. I don't need to define which phase of that substance is. Here, I needed to emphasize that I'm gonna do it so nothing is missing. So you work basically, at least in thermodynamics, you work with steam and gas. Same thing for the compressor. You compressed steams, Steams, yeah, H2O or refrigerant or some other steam, and gas. Okay, but here you can put anything. Okay, so whether it's gas, whether it's liquid or solid. Well, okay, so yeah, you can put solid, but it's a little bit different. You can put anything you want. Let me just put it like that. There could be certain problems regarding solids, but they are not very common. Okay, so after this, I'm gonna put some other thing. Let me just put it here that in this way, 3 is going in and 4 will go out. So the idea of building a heat exchanger is to heat something or to cool down something. Whether it's 1, 2, which is a hot substance, and you need to heat the cool substance that is going from 3 to 4, whether that's the case or the other way around, you don't care too much. I mean, maybe you care, but I'm thinking the heat exchanger doesn't care too much. You just put into thermal contact two flows, okay, of different substance in order to change the temperature of both of them, or maybe to change phase of one of them or both of them. But the idea is that you need to pass heat from one place to the other. I don't know which one is going to do that, but I'm putting that. Okay, that's the basic idea of that stuff. You are exchanging heat. There is not the best way to call it. You are not exchanging heat. Heat is just passing from the hot substance to the cool substance to the cold substance. Therefore, you cannot exchange heat, but nonetheless, that's the way these machines are named. Is not the best name, but nonetheless, you get the picture. Okay, conservation of mass. You will get that M1 plus M3, those things are going in, right? So should be equal to the things that are going out because we are working in steady state. M4 plus M2. Now these things are a little bit different. Okay, now conservation of mass will take you here. This is what the conservation mass will take you. But if you notice now from the drawing, maybe you notice that you can do this. Also, M1 equals to M2, yeah, and M3 equals to M4 because those two flows are not mixing between each other. So the same amount of one that is going in is going to be the same amount going out at 2. And the same thing for the flow 3, 4. Okay, so those guys will keep their own mass flows, okay, because you are not mixing them. Fine, so this is just because of how the drawing is done. There are other type of heat exchangers. I'm going to put them here. I will not analyze them because they are not very common, but you can say this. Maybe 1 is going in, maybe 2 is going in, and then now 3 is going out. And with that, I will put the conservation of mass of this guy is going to be m dot plus m2 going in equals to the things that are going out, which is just m3. Okay, these things are heat exchangers, but they are called mixers. It's not that I don't want them to see them or to take a look at them, but they are not, I mean, they are common in power plants, but it's not a typical heat exchanger in this course. Okay, so I won't talk about mixers. Going on with this heat exchanger, conservation of energy should be, so M1 H1 going in plus M3 H3 going in equals to M4 H4 plus M2 H2. That's it. These are my assumptions so that you know how I got to that place. Okay, first of all, this is adiabatic. This one is a consideration or the assumption more shocking because you will say, how is this thing adiabatic if it's called a heat exchanger? Well, what I can tell you is that this cube, okay, exists inside the heat exchanger. It's not something that you can say, well, you know what? This thing, now I am feeling it here because I am outside the heat exchanger and I'm feeling this heat that is going here. No, the heat exchangers are really well thermally insulated. so that they don't lose heat to the outside, but whatever heat exchanging is happening, it's happening in the inside of the of the of the machine or the device. Therefore, in a model sense, you don't put it Q, it's zero because you are not feeling any Q if you're standing right beside a heat exchanger. That could be the idea, okay? Just like a thermo or something. Well, okay, now another one. You don't have any mechanical power there. This thing is not turning any shaft or something. So no, so there is no work. You can also neglect changes in potential energy and kinetic energy. These guys are equals to zero. And also we are working in steady state. Hey, you missed one. You missed that this thing is isentropic. I would say that this guy is almost never isentropic. Okay, I would say that whether it's this or whether it's this, I can say, I will never say never happens or it always, no. But as a general rule, heat exchangers are, I would say, non-isentropic at all. Okay, so that's one of the basic difference with these other two machines that I left behind, turbine and compressor. Moving on, let's just move on to another. I'm going to use another color. So another machine. This machine is called the Nozzle. So a nozzle, it's not like a machine. I would say it's a converging pipe. So I will not dwell into, because you can have several geometries of nozzles, whether it's subsonic or the flow is supersonic. So I will talk only about the subsonic, and later I will try to say something about the subsonic. But nonetheless, so far it's just a converging pipe. So maybe you see that here you have one. So the flow at one sees a bigger area, and the flow at two sees or it's going through uh, um, lower value area. Okay, so it's getting smaller and smaller the area where the flow is going through as you walk from one to two. Okay, that's the basic idea. It's just a pipe that the area is being reduced. And with that, the basic idea is to accelerate something. So this is what you're looking for. That's the basic, that's the fundamental of a nozzle, to increase the velocity. Okay. Okay. So with that, I would say, let's just put conservation of mass. Conservation of mass is pretty easy. M dot equals to M2, which is equals to M dot. I'm just calling like that. And conservation of energy is M1 dragging around enthalpy plus kinetic energy. You cannot neglect kinetic energy here. It needs to appear. And this thing is going to be equal to M2 H2. Let me just move myself here a little bit to have a little bit of room. And B2 squared divided by 2. Okay, so that's the way that the conservation of energy should be written for a nozzle. Okay, I know that M1 and M2 are the same, so I could actually do this, but I'm not going to do it right now, okay, because I'm not solving any problem. I'm just telling you how to write this stuff. Okay, with that, let's just go to assumptions. These things have assumptions. Okay, so for assumptions, I would say, well, nozzles tend to be adiabatic. They do not produce any work. There is no shaft there going on. The changes in potential energy are equal to zero. You can neglect them. This is written for steady state. They tend to be isentropic. They tend. It's not always the case, but they tend to be that way. And what else? What else should I put here? I think that's it. Okay, so that's it for the nozzle. Yeah, I think I didn't miss anything about it. I should always be careful. Maybe there's something happening there. Well, okay. So what type of fluids can you be going like that? Well, you can put gases and you can also put liquids inside of them. Okay. I mean, you can put anything you want. Can you put solids? Well, yeah, you can put solids, but it's not very common to use nozzles with solids. What type of solid would you want to put? Or maybe a plastic that comes out from the furnace or something. Well, okay, so yeah, but that actually flows like a liquid. So I won't dwell into those type of things, but the idea is that you can use this for gases and liquids. It's not very this is not forbidden. Okay, now with that I will also talk about, with the same color, about some other, and I'm gonna do it fast, the diffuser. So the diffuser is just like the evil twin. Why evil? I don't know. But the twin of this is one, or this is going at one, and this is going at two. Well, let me just change it so that you do not get confused about where I have put this arrow. Okay, so here from 1 to 2. Okay, so now the pipe, it's increasing its area. So the diffuser is just an increase in area when you're flowing from 1 to 2. Okay, the basic idea of a diffuser is to increase pressure. That's why you put a diffuser, because you want to increase pressure. Conservation of mass will take you to M1 equals to M2 equals to M dot, okay? Conservation of energy, well, surprise, M1, H1 plus V1 squared divided by 2 equals to M2. Let me just get myself some room. H2 plus V2 squared divided by 2. So it's the same, actually it's the same type of formula. But then the problem will tell you if this is a diffuser or a nozzle, because you need to know which one is going up or which one is going down. For example, if you want to know something more about this, H2 is actually lower than H1 because you have used enthalpy in order to accelerate the flow. In this case, what you will be looking at most of the times is that H2 is higher than H1, because by deaccelerating or slowing down the flow, you will increase the enthalpy. Okay, that's what it's doing. And the assumptions are the same. So I'm just going to put it like this. Assumptions for a diffuser are, oops, just these same things. They are equal, okay? I'm gonna put it here, same assumptions. Okay, we still have 2 more to go. Well, they're not very difficult. None of these are really difficult, right? Maybe you will see and say, well, you know, this thing is not very, very difficult. Hopefully, that's what you're feeling at this, when you're looking at this. I'm gonna go with, oh, sorry. We'll do it with another color so that I'm emphasizing that this is just another. So pumps, or a pump. So pumps are for liquids. If you want to put inside that a gas, so you will talk about a compressor. The pump, most of the times, or well, I have known that this is the symbol for a pump. This is 1, okay? So 1 goes in and, you know, 2 goes out. It doesn't really matter where you put the arrows, okay? Or even the same, well, the drawing is a little bit important so that you can recognize how this is. There are also other ways to put it. There are books that put it like this, okay? So this is what they do. They put inside 1 and they put this 1, 2 outside, okay? That's another way to draw a pump. The pump, what it does, this is what a pump exists for. So it needs to increase the pressure. That's what it does, okay? Well, okay, and it has, I cannot put it here because of the drawing, but you need to be aware that you need to put into mechanical power or electrical power or work. Otherwise, the pump won't work, okay? That's the basic idea. Now with this, I will put conservation of mass. Conservation of mass for this fella is how much? This is M1 equals to M2. Conservation of energy equals, conservation of energy will give me the work equals to m dot, which is m1 or m2, whichever you want, multiplied by the specific volume times the difference of pressure between the entrance, or I would say between the discharge and the suction. Okay, that's are the names between 2 and 1. Okay, good. Now, assumptions, because this one looks a little bit different, right? You will say, well, you know what? I don't see the enthalpy there. I will try to explain you. So again, adiabatic. And you will say, oh, all of them are adiabatic. And I would say, well, yes. In a general view, you can model all these machines as adiabatic. Now, you can also say here that T1 equals to T2. Okay, you can also say that S1 equals to S2. You can say that the changes, this is delta, of the potential energy should be equal to, to 0, but I'm just taking that information for the kinetic energy. Okay, so they are not very relevant. Another assumption, okay, another assumption that I should put here, I'm going to put it here, that density at 1 equals density at 2. And with that, that's why I have this information here. That's why I have that. First of all, this thing is positive. I need to put in work, okay? So work goes in. Yeah, that's the first thing that you need to know. Then another thing, why you have this expression, because you don't see enthalpies here, and enthalpies are one of the most recognizable things in this type of problems. Well, you don't have it here because, I'm gonna put it here, maybe I can do it here. H, as a definition, the enthalpy is internal energy plus the workflow is pressure times the specific volume. Delta of H, it's delta of U plus delta of pressure times specific volume. Delta of H equals delta of U, fine, plus P delta P plus B delta P. Okay, I'm just doing this. This is just algebra, okay? Or properties of the operator delta. It's like I'm doing a derivative here. Well, okay, so if this thing is happening, therefore I can also say that the specific volume between 1 and 2 should be the same because I'm working with liquids. Since I'm working with liquids, these things are incompressible. Okay, so therefore this delta of the specific volume, it's 0. It doesn't change, okay? Now, delta U for liquids, it's the thermal capacity times delta T, or the change in temperature. And since pumps do not increase or reduce temperature, therefore you can say that in this machine, delta U is 0. Therefore, the only part of delta H that survives these assumptions is this one. So maybe you detect that you have the specific volume and you have delta P here, which is this one here. That's how you get this expression for the mechanical power or electrical power needed to power a pump. Okay, that's why you had this. Okay, cool. Just because it was liquid that you were doing that. One more, yeah, and I'm gonna use another fancy color, maybe this one. So I'm gonna put valves. Hopefully you can see this in this sheet of paper. So valves, well, valves are pretty easy. Okay, well, they are pretty easy to model. They are not very easy to design or something. You will put into 1, you will get out 2, and the basic, you can put whatever you want, whether it's liquid or gas or a vapor or a mixture or whatever. So it works fine, okay? So with valves, what you will have, the basic idea of a valve is to reduce pressure. You want this to happen. You want to reduce pressure. So what valves do is to regulate the flow, but they do it by decreasing pressure, okay? So that's one of the ways to know about it. Conservation of mass will take you to that M1 equals to M2. Conservation of energy will take you to the, what? To the, okay, yeah, sorry, because it's pretty simple. So the enthalpy is the same between 1 and 2. Hey, what about all the other things about the conservation of energy terms? Well, okay, so you want me to know what happened here? So I'm gonna put assumptions. Assumptions for that one. You can say that about the adiabatic, you can say that it doesn't have any shaft turning around or yeah, so you don't need any mechanical power there, not in, not out. You can also say that the changes in potential energy can be neglected just as the kinetic energies can be neglected. Okay, these guys are around zero. You can never say this. I think this is the only time that I can say never. A valve is never isentropic. Okay, is there something missing? Well, you can put this also. Um, I have used this one. Yeah, I have used this one. So yeah, that's about it. That's basically about this device. I was gonna say machine. It's not like a machine, but yeah, in some sense, this thing is a machine. Okay, so this was pretty easy, right? To model this pretty easy. What it does, it reduces the pressure. That's the basic idea. Hey, what about the temperature? I don't know. You need to do problems in order to know whether the temperature is decreasing or increasing. But the basic idea in order to do this is that you need to follow this rule that the enthalpy is not changing. Okay, so it wasn't too hard, right? We're gonna use this in order to do problems regarding all these devices or machines, okay? So that's enough for today. We'll see you in some other chance that we have. So see you guys.